Bismillahirrahmanirrahim. Today we will prove the three equations, which is S is equal to R theta and V is equal to R omega and A is equal to R alpha. This is the relationship between linear and angular acceleration, and this is the relationship between linear and angular velocity, and this is the relationship between linear and angular acceleration. To prove this equation, as three units are generally used to express angular displacement, namely degrees, revolution and radians. We are already familiar with the first two as regards radian, which is SI unit of the angular displacement. Consider an arc of length S of a circle of radius R, which subtends an angle theta at the center of the circle, and its this is angle theta and this is the radius of the circle. This is point P1 and this is point P2, and this is the center of. The value of theta of angular displacement in radians is given by theta is equal to length of arc divided by radius into radians. So the theta is equal to arc is here, this arc is S, so S divided by R into radians. So theta is, so here S is equal to R theta, where theta is in radians. So in equation we write S is equal to R theta, which is the required equation. If this OP is rotating, the point P covers a distance S, which is equal to 2 pi R. S is equal to 2 pi R. By putting this value in this equation, the theta in radians is equal to S divided by R radians. So theta is equal to 2 pi R divided by R into radians. So theta is equal to 2 pi radian, which is equal to 360 degree. 2 pi radian is equal to 360 degree. So 1 radian is equal to 360 degree divided by 2 pi, which is equal to 57.3 degree. This is the value of 1 radian. Now, and the required equation was this, which is S is equal to R theta. Now what? Prove the equation 2, which is V is equal to R omega. Here this is equation 1, this is equation 2, and this is equation 3. Now prove equation 2, which is V is equal to R omega. Consider a rigid body rotating about z-axis with an angular velocity omega as shown. Here, this is z-axis, and here this is center, and here a body is rotating. This is radius and this is point P. So here, and it moves in this direction with angular velocity omega. So imagine a point P in the rigid body at a perpendicular distance r from the axis of rotation. OP represents the reference line of the rigid body. As the body rotates, the point P moves along a circle of radius with a linear velocity v, whereas the line OP rotates with angular velocity omega. As shown here, this is axis of rotation and body rotates. This is radian, this is point O, and this is point P, and this is point P2. This is point P1 and this is point P2, and this is arc S. This is theta, and it moves with linear velocity v and with angular velocity omega. Its angular velocity is omega, linear velocity is v, and angular displacement is theta, radius is r. So here, as we are interested in finding out the relationship between omega and angular and linear velocity, as the axis of rotation is fixed, so the direction of omega always remains the same, and omega can be manipulated as a scalar. As regards the linear velocity of the point P, we consider its magnitude only, which can also be treated as a scalar. Suppose during the course of its motion the point P moves through a distance P1, P2, which is equal to delta S in a time interval delta t, during which reference line OP has an angular displacement delta theta radian and delta theta in radians. During this interval, delta S and delta theta are related by equation 1, which is S is equal to R delta, which is delta S is equal to R delta theta. So here, dividing both sides by delta t, delta S divided by delta t is equal to R into delta theta divided by delta t. If in the limit when delta t tends to 0, the ratio delta S divided by delta t becomes v, and the magnitude of the velocity with which point P is moving on the circumference of the circle. Similarly, delta t theta divided by delta t represents the angular velocity omega of the reference line. OP is of the reference line OP. So this equation becomes V is equal to R theta. V is equal to R omega, which is the required equation 2. So in this figure, it can be seen that the point P is moving along the arc P1, P2. In the limit when the delta t tends to 0, the length of the arc of the direction of tangent to the length of arc P1, P2 becomes very small, and its direction represents the direction of tangent to the circle at point P1. Thus, the velocity with which point P is moving on the circumference of this on the circumference of the circle has a magnitude v and its direction is always along the tangent to the circle. That's why the linear velocity of the point P is also known as tangential velocity. Tangential velocity. Similarly, equation 2 shows that if the reference line OP is rotating with an angular acceleration alpha, the point P will also have a linear or tangential acceleration at. The point P will also have a linear or tangential acceleration. Using equation 2, it can be shown that the two accelerations are related by this equation, which is given by at is equal to r alpha. And which is the required equation. Now, what are the equations for angular motion? Equations for angular motion has three equations for linear motion linear motion are Vf is equal to Vi plus At, which is first equation of motion, and second is S is equal to Vi t plus half At square, and third equation of motion is 2As is equal to Vf square minus Vi square. So this is second equation of motion and this is third equation of motion. So here by first equation of motion of linear motion, which is Vf is equal to Vi plus At. From this equation of linear motion, the equation of angular motion is here. In angular motion, as this is V is equal to r theta, r omega, and A is equal to r alpha. So by putting value of V and A in this equation, in equation 1, r omega f is equal to r omega I plus r alpha t. Common r from both sides, so r into omega f is equal to r into omega I plus alpha t. So here, by rearranging the terms, final angular velocity is equal to initial angular velocity plus acceleration into time interval. So this is equation of angular motion. First equation of angular motion, which is omega f is equal to omega I plus alpha t. And from second equation of linear motion, which is S is equal to Vit plus half At square. So here S is equal to r theta and V is equal to r omega and A is equal to r alpha. So by putting this value in this equation, these three values in this equation, r theta is equal to initial omega I, r initial omega into t plus 1 divided by 2 alpha r alpha into t square. So common r from both sides, r theta is equal to r into initial omega t plus 1 divided by 2 acceleration and t square. So here theta is equal to t plus 1 divided by 2 alpha t square. This is the second equation of angular motion. The third equation for angular motion is third equation of linear motion is 2as is equal to vf square minus vi square. So 2 into alpha into theta into r square. 1r is with alpha, r alpha and r theta is equal to final omega r square minus initial omega r square. So 2r square alpha into theta is equal to final omega square r square minus initial omega square r square. So common r square from both sides. So 2 alpha into theta into r square is equal to r square into final omega square minus initial omega square. So 2 alpha theta is equal to final omega square minus initial omega square. This is the third equation for angular motion, which is the required equation. Thanks.